We move through it, we live in it, and honestly, we barely ever give it a second thought. But what is space? Is it just nothing? The empty void between stuff? Well, this question, which seems so simple, has actually sparked some of the biggest debates in all of science and philosophy. And today, we're going to get into that story. So, let's start with what we all probably learned in school. A three-dimensional continuum containing positions and directions. Sounds pretty straightforward, right? Kind of like a simple grid you can use to map out where everything is. But, as you're about to see, that simple definition is just the very, very tip of a cosmic iceberg. Because right off the bat, we run into this massive conflict. Is space a real thing? Like, an actual container that would still be here even if you took everything else out of the universe? Or is it just an idea? Just the way we talk about how far apart things are and in what direction? And believe it or not, this exact question set the stage for one of the first great showdowns of modern science, pitting two of the heaviest hitters of the 17th century against each other. Okay, so in one corner, you've got Sir Isaac Newton. For him, it was simple. Space was the ultimate stage. It was absolute, it never changed, and it was always there. A fixed physical background where all the action of the universe happens. But in the other corner, Gottfried Leibniz was like, no way, that's just nonsense. For him, space was purely relational. It's just an abstract concept we use to describe how things are arranged. You take away the things, and poof, space is gone too. Leibniz had this fantastic way of explaining it. Think about a family. All the relationships, mother, brother, cousin, they're all real for sure, but they don't exist by themselves. You can't just have cousinness floating around in a room without any actual cousins. Well, Leibniz said space is exactly the same. Take away every object in the universe, and space itself just vanishes. But here's the thing about Newton. He wasn't just some guy thinking in a room. He was an experimentalist. And he was sure he had stone-cold proof that space was a real physical thing. And his proof? It came from something you'd never expect, a spinning bucket of water. Okay, let's walk through this, because it's pretty brilliant. First, you've got a still bucket of water, and the surface is perfectly flat. Simple enough. Next, you start spinning the bucket. As the water starts to spin along with it, the surface curves inward. It gets all concave. But now, and this is the genius part, you suddenly stop the bucket. But the water inside, it keeps on spinning, and its surface stays curved. And here is the puzzle. Think about that final moment. The water is spinning, but the bucket has stopped. So there is zero relative motion between the edge of the water and the walls of the bucket. And yet, the water is still curved. That means the curve can't be caused by the relationship between the water and the bucket. Which leads to the million-dollar question. If the water isn't spinning relative to the bucket, what is it spinning relative to? What's out there that's causing the forces that make the water climb up the sides? And Newton's answer was a game changer. The water, he said, is accelerating relative to absolute space itself. This one experiment seemed like the final knockout punch. It proved space was a real physical thing. And for the next 200 years, that was pretty much the final word. Case closed. Or was it? Let's jump ahead to the 18th century, because the whole story is about to take a wild philosophical turn. A German philosopher named Immanuel Kant came along and proposed a third option that was just completely out of left field. So Kant argued that space isn't something we discover out there in the world at all. Instead, he said it's a fundamental piece of how our own minds work. He called it a pure a priori form of intuition, which in plain English means it's like a pre-installed mental framework. Think of it like this. Space is the operating system for your brain. It's the built-in software we use to organize all the information coming in from our senses. We don't perceive the world and then figure out that space exists. We use our built-in idea of space to even make sense of the world in the first place. For Kant, it's just part of the hardware of being human. So for a while, the debate went quiet. But then, in the 19th century, a bunch of mathematicians came along and basically blew the doors off the whole thing. For over 2,000 years, everybody just assumed that the geometry of space was the flat, predictable geometry of Euclid. Well, they were about to show that there were other options. So by challenging just one of Euclid's ancient rules, the one about parallel lines, these mathematicians discovered entire new forms of geometry that were perfectly logical.
They described worlds where space itself could be curved, worlds where the angles in a triangle don't add up to 180 degrees, or where lines that look parallel could actually meet. All of a sudden, space wasn't just one thing. It could be many things.
And this wasn't just them doodling in a notebook. It led directly to this incredible real-world question. What is the actual shape of our universe? Are we living in a flat, boring Euclidean space, or is it curved in some way we can't see? For the first time, the very geometry of reality was up for grabs. And this is where the final hero of our story enters the picture. In the early 20th century, a young patent clerk named Albert Einstein would take all of these ideas from Newton, from Leibniz, from Kant, and from these mathematicians and weave them all together into something totally new and revolutionary. So first, in 1905, he publishes his theory of special relativity, and he fuses space and time together into one thing, space-time, a single four-dimensional fabric. Then, 10 years later, he drops his masterpiece, general relativity, and he tells us what this space-time fabric actually does.
And here is Einstein's absolutely mind-bending insight. For centuries, gravity was seen as this invisible force, right? Pulling things together. Well, Einstein came along and said, nope, gravity is not a force at all.
It's the curvature of space-time. Yeah, you heard that right. Heavy things like planets and stars don't pull on other objects. What they do is they bend and warp the very fabric of space-time around them. And other objects, they're just following those curves. The Earth isn't being pulled by the sun. It's just following the straightest possible path through the curved space the sun creates. I mean, this completely changed the game. Einstein gave us our modern picture of space, not as some empty box, but as the very fabric of reality itself. So Einstein's space-time is this brilliant mix of the old ideas. It's a real physical thing, just like Newton's absolute space. But its shape and its behavior are determined by the matter and energy inside it, which sounds a whole lot like Leibniz's relational view. It's not a passive stage, it's an active, dynamic player in the cosmic drama. And this isn't just a cool theory. This is the reason your GPS works, constantly correcting for how Earth's gravity literally warps time and space. And this dynamic view of space goes all the way back to the very beginning. Our best models tell us that space itself was created 13.8 billion years ago in the Big Bang. It wasn't an explosion in space, it was an explosion of space, which has been expanding and cooling down ever since. And this leaves us with one last truly wild question to chew on. If the entire universe, all of space, is expanding, what is it expanding into? The question itself might not even make sense because it suggests there's an outside to space, which may not even exist. It's a question that just goes to show how far we've come in this story, from thinking of space as an empty box to seeing it as the dynamic, expanding fabric of our entire existence.